WINDPOWER students, Dr. John Schrage here, and I'm just giving you a quick lecture today, a relatively short one, associated with just a couple of pages in Chapter 2 that are about what we talk about when we're in the atmospheric sciences when we talk about different scales of motion. There's lots of things going on in the atmosphere at any given time, and it isn't necessarily like the big things are more important or the little things are more important or anything like that. There are things that happen on a wide variety of scales, any of which, and all of which, could be very important when we're talking about the production of wind power by turbines. And to understand what we're talking about when we say wind, scales of motion in the wind, let's first start out by talking about different scales of motion in water. Let's say you were some kind of scientist and you were studying the motion of water in the ocean. Well, actually, there's lots of different kinds of motions going on at the same time. For example, there are these little ripples that are moving along on top of the ocean. But there was also like the big swells and waves that are like the kind of things a surfer would be riding. But there's also tides. I mean, over the course of a day, there's two high tides and two low tides that are changing the overall height of the ocean. That's a type of wave as well. Well, in a certain way of thinking about it anyway, it's a type of wave. And those are all important in different ways. Just to give you an example, it's actually ripples at the surface of the ocean that are responsible for a lot of the friction between the atmosphere and the ocean. Ripples don't look like all that much, but they're steep. Ripples are actually very steep and they're everywhere. So they are creating a lot of friction between the atmosphere and the surface of the ocean. Whereas like tides would have enormous consequences for like the large-scale currents that are going on in like a bay or an estuary, and the waves would be important for different kinds of purposes. It's not like one is important and the others are not, and they could all be happening at the same time. There can be ripples, in fact in general there are ripples across the top of the waves, which are themselves riding on top of the very large-scale changes that are the tides. All of them are important in different ways. Not all of them necessarily affect everything. Ripples don't really have much to do with currents, at least not directly. Tides don't have very much to do with the surface roughness of the ocean, but overall, all three of them are important just in different ways. And in the same way, if I'm looking at this wind farm down here at the bottom here, they're all important in different ways. All these different kinds of motion here. I mean, the amount of wind power, of wind energy that will be available to these turbines is going to vary a lot. Like over the course of the day, that is the diurnal cycle of the wind, where like, you know, maybe at night there's relatively calm conditions and during the day the wind could be quite strong. In fact, it could be quite gusty, where we'd even have like, you know, variability within the day. You know, from minute to minute or from hour to hour. But I wanted you to snag on that vocabulary word there, diurnal, as in over the course of a day. There could be big differences in the amount of wind available for this wind farm based on weather patterns that are happening, like the arrival of cold fronts or a high pressure system that's moving in. The right powerful vocabulary word for that is there could be on the synoptic scale. We're going to see this word more in a little bit, but the word synoptic is a hard word. Synoptic means like overview. You probably, for example, have taken theology classes and you know about the synoptic gospels. These are the gospels in the Bible that kind of tell the story of the broad outlines of Jesus' life, right? He was born, he did these certain things, he went and got crucified, and then he rose from the dead. They tell the broad outline of the story of his life, the synoptic gospels. In the same way, synoptic in the sense of atmospheric sciences means like overview. The broad idea. There's low pressure systems over here, there's high pressure systems over here, there's a cold front coming through over here. The big large scale overview is what this means. This word synoptic is the same set of Greek loan words that gives us like synopsis. Okay? It gives you the overview. And we'll see more about that in just a little bit here. There could also be differences in the amount of wind energy available to this farm in the annual sense, like over the course of a year from one season to another. In some parts of the world, the winds would be much stronger, say, in the winter than they are in the summer. That's a little bit hard if you're to think about if you're thinking about like Midwest. Okay, in our part of the world, oh, I don't actually have the statistics in front of me. It could very well be that it's overall a little windier in the winter than it is in the summer in Omaha. I actually don't know. And that could actually have important consequences for your wind farm here. But on the other hand, like some parts of the world, like in the tropics, for example, a lot of places have a monsoon climate, or they have a type of winds in the winter called the harmattan winds. We might learn about that later. Where, you know, it could be quite windier in the winter than in the summer or something like that. I mean, that can be a very important deal that gives us an annual cycle to the amount of wind power available. There can even be interannual variability, the difference between one year and another. Some parts of the world have very large interannual climate variability, as in one year's weather is very different than the others, okay? This can be due to the kinds of phenomena that we're going to be talking about towards the end of this module, like El Nino or the North Atlantic Oscillation. But there are other sources of interannual variability as well. Maybe in one year, your wind farm will have a great deal of power available to it because of the wind weather patterns, and another year it could be quite different. There's a lot of different scales of wind variability here, and there could, of course, be lots of interaction between these scales. For example, maybe there's a change to the diurnal cycle over the course of the year. Maybe in the winter, you tend to have stronger winds at night and weaker winds during the day, and in the summer, you tend to have weaker winds at night and stronger winds during the day in your particular climate regime. Oh, that would be something to know, right? I mean, if you're needing to figure out the electrical load and the electrical yield that your wind farm is going to be able to produce, you would need to know that kind of ways in which different scales of motion in the atmosphere are interacting. In general, there will be multiple scales of motion interacting at the same time. I mean, for example, let's say some kind of storm system is moving in. All right, we'll be more precise about, I hate words like storm system, okay? All these things have names. But for now, let's say some kind of storm system is moving in, and you know that over the course of the next few hours, in general, the amount of wind energy that's available will be larger. But, you know, from minute to minute within that storm system, there can be wind gusts. And those wind gusts might be changing, obviously, the amount of wind energy available quite a lot. And that all might have important implications for how you're producing wind power at your turbine. You know, the overall increase in the amount of wind might be something very useful to you in terms of how much power you're producing, but maybe individual gusts within the storm might be exceeding the wind speed range over which it's safe to operate the turbine, and you need to actually shut the turbine down during that period. Okay, so we have some issues here about how these scales can interact. Now, your textbook actually throws together a little table, which I have reproduced here in PowerPoint, and I've made it kind of a little bit different than the format they had it set up in, because I wanted to show you how these scales are sort of nested inside of each other. That's an aspect of it that is not exactly clear in the table in your textbook. Microscale is going to be inside of Mesoscale, which is going to be inside of Synoptic. Weather features that are microscale are embedded within features that are mesoscale, and mesoscale features are embedded within scales. So I tried to kind of illustrate that using this somewhat cheesy PowerPoint graphic here. Alright, so I've sort of reproduced this table, and we're going to kind of pick this table apart over the next few minutes here. And what I'm going to do is I'm going to first zoom in and talk about microscale features of the atmosphere. Now, your book, I don't entirely agree. There's not a solid, 100% this is the canonical definition of what we mean by microscale, but your book is saying that these are going to be features of the atmosphere like storms or wind features in the atmosphere with a length scale on the order of 10 to the second power meters, or hundreds of meters. And they're going to be features that only last on the order of a few minutes to a few hours. A few hours, frankly, seems a little generous on there as to how long we're talking about. And the example they cite in the table of a microscale feature of the atmosphere is a little bit hard to understand. They said thunder showers. Now, to understand what we mean by thunder showers, I don't mean a thunderstorm. TV meteorologists often use the word thunder showers and thunderstorms kind of interchangeably. It's important to know from context that the author is from Denmark, in the context of like European meteorology, they use the word rain shower to kind of mean like a little downpour inside of a weather system. Okay, so like it's been kind of lightly raining all day, but for a few minutes there was kind of a downpour. Okay, that's what they're talking about here where they say thunder showers. Again, it's kind of important to know that he's Danish to have known that. I used to, I don't know if I've ever mentioned before, but part of my job used to be on site at a university in Germany. And so I would spend the summers there and the school year at Creighton. And so I happen to know that that's the way they use the word thunder shower in European meteorology. Anyway, so that's what they were talking about. But, you know, honestly, that's maybe not the handiest example of microscale weather features. I wish I had given more. If I were thinking about microscale features of the Earth's atmosphere that make us think in the context of wind energy, I would say gusts. Gusts of wind are generally microscale. They are actually difficult to envision what's going on, but gusts of wind are usually little swirls in the atmosphere that are embedded in larger scale features of the atmosphere. But if we could somehow see the air, we would see it is swirling. And so as you stand in, you know, one place, one of these little eddies, one of these little swirls, as it approaches you, you are, you know, maybe where the wind is coming toward you for a while on the eddy, and you feel a strong gust of wind, and then as you are on the part of the eddy where the wind is moving away, you know, where now the flow is weaker, you are seeing the period after the gust or whatever, you see these swirls of motion. We're obviously going to talk about gusts of wind more in later modules, but that idea of these sort of, you know, swirling features in the atmosphere that have a radius of maybe 100 meters or something like that, and we can't see them with our eye, but as they move by, you get a period where the wind is stronger and then a period where the wind is weaker. Those are gusts. They are certainly microscale. Dust devils would be another really good example. Dust devils are sort of a more extreme version of wind gusts. I mean, they're the same sort of thing where you can actually now visualize, because you see the dust that's being picked up, and you can actually see the swirling motion of the wind as it goes by. These are microscale features. Microscale climate might be things like it is colder and more damp on the north side of your home than on the south side of the home, so you have trouble growing tomatoes on the north side of the house, but it is easy to grow tomatoes and cucumbers on the south side of the house, okay? The garden on the north side is just too cool and damp, okay? On the scale of a few tens of meters or something like that, there's a difference between the climate on the north side of the house than on the south side of the house. Just due to like the shade of the house or whatever. Okay, mesoscale. Mesoscale encompasses things that are microscale happen within weather features that are mesoscale. Meso is a Greek prefix that means something like middle. Okay, so this is sort of the middles of these scales here. We saw the Greek prefix meso before when we talked about the mesosphere. It was kind of the middle atmosphere. Your book uses this number of 10 to the 5th power meters. I don't think in terms of 10 to the 5th very well. I know that my exponent rules tell me that I can subtract 3 from that. So 5 minus 3 is 2. 10 to the 2nd are hundreds of kilometers. You can always subtract 3 from the exponent and change it from meters to kilometers. So this is like a few hundred kilometers. It's on the time scale of things like hours. These are features of the Earth's atmosphere that are more persistent than the microscale features and larger than the microscale features. And the example that your textbook points out is sea breezes. Now, if we were teaching this class at, you know, the University of Florida or something like that, where sea breezes were a more common phenomenon, we might be more comfortable. I could probably leave it at that, but let's face it, we're at Creighton. Many of the students who are taking this class are Midwesterners. We may not have so much familiarity with the idea of sea breezes. We'll learn more about how sea breezes work in a future module. They certainly have wind power ideas associated with them. I mean, if you want to set up turbines near a coastline, either on land or at sea, you're going to need to know about land breezes and sea breezes. But if I wanted to actually talk more about the kinds of things you and I have familiarity with, on the mesoscale, I would say there are things like thunderstorms or even groups of thunderstorms. If an actual, like severe thunderstorm is coming through, the size of the thunderstorm might be on the order of like 100 kilometers. 100 kilometers is what, about 60 miles across? That'd be a fairly big thunderstorm, but certainly a very appropriate size for like a cluster of thunderstorms or a line of thunderstorms that was coming through. Or like lake effect snow. We don't tend to get lake effect snow in Omaha, but you know what I'm talking about when I say lake effect snow. This is that big dumps of snow that they get off like the Great Lakes. Okay, off, the downwind side of the Great Lakes tend to get these kind of snow weather patterns where they get these heavy snowfalls. These lake effect snowstorms, they're only, maybe 100 kilometers, 200 kilometers across. They are a relatively medium-sized weather feature. Inside of the lake effect snowstorm, there can be gusts. There can be microscale features within the lake effect snowstorm. Within the thunderstorm, there are winds, gusts, there are tornadoes, things that are microscale in size and in duration. But those things are nested within these mesoscale features. Moving up and highlighting in white here, the next scale up is our synoptic scale. This is that kind of large scale overview type scale that we get that describes the atmosphere in terms of features that we see from weather observations that are far spaced apart, and these are features that are, let's see, 10 to the 6th meters means 10 to the 3rd kilometers, so we're talking like thousands of kilometers across. These are going to be broad features that are spanning an area, let's say several states wide. They typically last on the order of like days. Doesn't necessarily mean they last days at one particular location, but like as these features move, the total life cycle of their features are going to last on the order of days. And the textbook example of these kinds of synoptic features will be cyclones and anticyclones. Now in the next, I think it's the next, maybe it's one more after that, lecture in this module, we're going to learn a lot about cyclones and anticyclones. But for now, I'll just tell you that these are those broad areas of low pressure, in the case of cyclone, or high pressure in the sense of anticyclones, that you see on a daily weather map. When you turn on the Weather Channel, and there's L's and H's on the map, those are cyclones and anticyclones. And they're broad areas of low pressure or high pressure that are controlling the weather over the area of like the Midwest or the Southwest or something like that. They span multiple states. You may not have so much experience with like what I mean by cyclones and anticyclones, but other examples of synoptic scale weather features would be things like hurricanes. Okay, now the storm itself of a hurricane is actually maybe not quite thousands of kilometers wide. I mean, hurricanes are actually kind of surprisingly small, but like the track of the hurricane, it covered an area thousands of kilometers long. Or like a cold front and warm fronts. Okay, I got like a weather map down there. You don't know very much yet about cold fronts and warm fronts and so on, but odds are you at least are aware, hey, if I turn on a weather channel or I look at the weather page at the back of USA Today or something like that, I see these fronts on the map, and they span thousands of kilometers. The actual front itself is not terribly wide, but it spans an area thousands of kilometers long. These are large-scale things that provide kind of this overall synopsis of the weather. I mean, if I actually looked closer at that synoptic scale hurricane, I'd see that embedded within it there are mesoscale structures like individual thunderstorms or even like lines of thunderstorms with the rain bands around the hurricane and stuff like that. And if I zoomed in even closer, I could see that there's things like gusts and maybe tornadoes or things like that embedded within the mesoscale feature. See how they're all kind of nested inside of each other? And finally, there's this global scale, or planetary scale, to use the terms kind of interchangeably here, where we're talking about things, let's see, 10 to the 7th power meters means 10 to the 4th power kilometers. We're talking almost on the order of like tens of thousands of kilometers. These are very large scale features of the Earth's atmosphere that persist for weeks or longer. And I hate the example that they give you because they say planetary waves, and that probably is not helpful to you. When we say planetary waves, what we're talking about are these meanders that happen in the flow, particularly at the level of the jet stream, which is, we haven't learned about the jet stream yet, but it's the very strong, I hate the expression rivers of air, but you get the idea that way, that are up near the height of the tropopause. And we'll learn quite a bit about what they're all there for and so on. But as these rivers of air flow through the atmosphere, they sort of meander north and south. That is a type of wave. It's very different than the kind of waves you're experienced with like the beach or something like that. But these waves of the jet stream as it meanders north and south are a phenomenon in the atmosphere. They are very closely related. In these waves in the jet stream is where cyclones and anticyclones happen. So inside of these planetary scale waves that are maybe tens of thousands of kilometers wide, there are synoptic scale features like cyclones and anticyclones that might be more like 1,000 kilometers across. And embedded within the cyclone, there can be mesoscale features, and embedded within the mesoscale features, there can be microscale features. Okay. Another example of a type of global scale or planetary scale feature would be El Nino. Now we're going to have a lecture later in this module actually about El Nino and how it is a global scale phenomenon in the Earth's atmosphere. It changes, the global distribution of how winds and storms are being distributed across the Earth. It's related to changes in the temperatures of the ocean that happen on very long scales. It takes like a year to a year and a half for a El Nino event to play out in the Earth's atmosphere, actually in the Earth's ocean atmosphere system. It's a system that connects the ocean to the atmosphere. All these different scales are really detailed, and all of the definitions are somewhat loosey-goosey in that table here. I don't want you to think that like wind gusts can only be this wide, or they can only last this long. It's more like there's a probability distribution. It's less likely that there'd be ones bigger than that or smaller than that, but they can happen. There can be relatively large cyclones. There can be relatively small ones. There's a certain preferred size, but they have a range of sizes, a probability distribution of sizes. But this kind of helps us recognize that there are kind of a hierarchy, if you will, of sizes of things that happen in the Earth's atmosphere, and as a general rule in the atmosphere, the bigger a phenomenon is, in terms of like how many meters it spans, in general, the longer it will last. And you can, of course, go back and look at that table in your textbook, or the one that's been in these slides, and see that that pattern holds quite well. There is, in general, one main exception to that. There is, in general, one way to quantify that. In general, for every 1 meter that a weather phenomenon is wide, it is about 1 second in length. So something that is approximately, 10 to the 5th power meters wide will be 10 to the 5th power seconds long in terms of how it lasts. Now, you can go back and actually look at that table and see, well, that pattern sort of holds, but it's actually off by an order of magnitude on this scale and whatever. It's a good rule of thumb, though. If you are looking at a feature, if something happens in the atmosphere that results in your wind being greater than you expected for 10 to the 3rd power seconds, in general, you should be looking for something that's about 10 to the 3rd power meters long that caused that. Okay, that's a good point. It's unlikely that something that only lasted a few seconds was as big as many states. Nor is it likely that something that is persistent and lasting for many hours is only maybe a few tens of meters wide. That just isn't, in general, the way the atmosphere works. Alright, anyway, I hope this little overview of how scales of motion are described in the atmosphere helped. Let's answer a couple quick questions before we send you back to Blue Line. Question 1. Put these scales of atmospheric motion in order from largest to smallest. Synoptic, planetary, micro, meso. And then I have 4 different permutations of those 4 options. Which of those is the right way to order the scales of motion from largest to smallest? Make a choice from your 4 options and get some feedback before you move on to question 2.